Tonight, we're going to explore something that sounds simple, but is actually one of the most perspective-shattering concepts in all of science: the true scale of time and how short human history really is. You've probably heard phrases like deep time or cosmic time before. Scientists talk about billions of years, the universe being ancient, but here's what most people don't realize. When you actually comprehend the true scale of time, when you understand how recent we really are, it doesn't just change numbers in your head. It changes everything about how you see yourself and your place in existence. If you compress the entire history of the universe into a single year, all of recorded human history, everything from the first cities to space travel, fits into the final seconds before midnight on December 31st. Not minutes, not hours, seconds. By the end of this journey, you're going to understand exactly what this means and why this perspective might be the most important thing you can learn about reality itself. Before we dive in, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now let's begin. Close your eyes for a moment and imagine something impossible. Imagine that you could hold the entire history of the universe in your hands like a book. Not just any book, but a calendar. A single year. 365 days that contain everything that has ever happened, from the first moment of existence to this very second as you listen to these words. This is not just a thought experiment. This is a tool that scientists use to make sense of something that our minds were never designed to comprehend: the true age of everything around us. We call it the cosmic calendar, and it might be the most honest clock that humanity has ever built. It tells time in a way that strips away every comfortable illusion we carry about our place in the story of existence. In this calendar, January 1st begins with the Big Bang. Not metaphorically, but literally. The first second of the first minute of the first hour of the first day represents that moment 13.8 billion years ago, when space and time themselves came into being. The calendar doesn't ask you to imagine what came before, because before is a word that loses all meaning when time itself has not yet begun. It simply starts the count. And where does this calendar end? December 31st at the stroke of midnight. Right now. This moment. As you hear these words, you are living at the very edge of December 31st, in those final precious seconds before the year turns over. Every breath you take, every heartbeat, every thought that passes through your consciousness is happening in the thin air of the calendar's end. But here's what makes this calendar so brutally honest, so impossible to dismiss once you truly understand it. Your entire life, from the day you were born to this very moment, occupies less than a single second of this cosmic year. Not a minute, not an hour, not even multiple seconds. A fraction of 1 second. If you live to be 100 years old, your entire existence will have lasted roughly 1/3 of 1 cosmic second. The calendar doesn't stop there in its relentless honesty. All of recorded human history, everything we know about civilization, every empire that has risen and fallen, every war that has been fought, every book that has been written, every piece of music that has ever been composed, every discovery that has ever been made, all of it fits into the final 10 or 15 seconds of December 31st. The pyramids were built in the last few seconds. Rome rose and fell in the last few seconds. The Renaissance, the Industrial Revolution, the Space Age, all compressed into those final heartbeats before midnight. This is what we mean when we talk about deep time. Not just that the universe is old, but that it is old in a way that makes our intuitions about time completely useless. Your nervous system evolved to track seasons, to anticipate the migration of herds, to remember where you left food stores from one winter to the next. It was never meant to grasp billions of years. It cannot do it. The numbers become meaningless. 13.8 billion might as well be infinity to the part of your brain that actually experiences duration. But the calendar can do something that raw numbers cannot. It can give you a framework for feeling the weight of deep time without being crushed by it. When you think of the universe beginning on January 1st, you can actually picture January 1st. You know what it feels like to live through a full year. You understand the rhythm of seasons, the slow transition from winter to spring to summer to fall. You can use that familiar framework to hold something unfamiliar, the entire lifespan of everything that exists. Think about what this means for perspective. If the Big Bang happened on New Year's Day, then the first stars didn't begin to shine until late January or early February. Our own galaxy, the Milky Way, didn't begin to take its current shape until perhaps March or April. The solar system, our cosmic neighborhood, didn't form until early September. Earth itself is only a few days older than that, cooling and solidifying as September progressed. Life on Earth didn't appear until late September or early October, and for most of the year that followed, that life remained invisible to the naked eye. Just microscopic organisms learning the basics of chemistry, reproduction, and survival. The first complex cells didn't emerge until November was well underway. Animals with backbones didn't appear until the third week of December. Dinosaurs ruled the Earth for barely a week, from December 24th to December 30th. And then, in the final day of the year, in those last 24 hours of December 31st, mammals began to diversify and spread. Human ancestors, the earliest primates, appeared only in the evening hours of December 31st. Modern humans, with brains capable of art and language and abstract thought, arrived in the final minutes before midnight. Agriculture was invented in the last minute. The first cities were built in the last 30 seconds. The scientific method was developed in the last 10 seconds. You were born in the last tiny fraction of the final second. This is the gift and the curse of the cosmic calendar. It shows you exactly where you stand in the vast procession of time, but it doesn't tell you what to feel about that position. You might feel small, insignificant, like a brief flicker in an enormous story that was unfolding long before you arrived and will continue long after you're gone. That's one way to interpret your place near midnight. But there's another way to see it, one that might be even more profound. You are living at the most interesting moment in the calendar. You exist at the only time when the universe has become capable of understanding itself. The calendar is honest about your brevity, but it's also honest about your rarity. In all those billions of years, in all those cosmic months and weeks and days, consciousness capable of grasping deep time has emerged only in these final seconds. You are not just living at the end of the year. You are living at the moment when the year finally learned to count its own days. Why do large numbers fail us so completely when we try to understand time? The answer lies in how your brain actually processes magnitude. When you hear the word million, something happens in your mind. You can picture it roughly. $1 million feels different from $1,000. You understand that it represents abundance, significance, a quantity that matters. But when someone says billion, what happens then? The word bounces off your consciousness like light off a mirror. Your brain hears it, processes it as very large, and then immediately stops trying to feel what it actually means. This isn't a failure of intelligence or education. This is how human cognition works. Your ancestors needed to distinguish between 3 predators and 7 predators, between enough food for 2 days and enough food for a week. They never needed to feel the difference between 1 million and 1 billion, so that capacity simply never evolved. The neural architecture that serves you so well in daily life becomes completely useless when confronted with cosmic timescales. 13.8 billion years might as well be infinite years, because your brain treats both numbers exactly the same way, as quantities too large to truly comprehend. But calendars work differently. Calendars tap into something much deeper in your cognitive architecture, something that evolved over millions of years of seasonal change and cyclical time. You don't just know what a year feels like, you've lived through years. Your body remembers the rhythm of seasons. You understand viscerally how long it takes to move from January to December, how the days grow shorter and then longer, how winter feels endless until suddenly spring arrives with its subtle warmth and lengthening light. When we use the cosmic calendar, we're not asking your brain to do something impossible. We're asking it to do something it already knows how to do: navigate the familiar rhythm of months and days and hours. The framework itself provides the structure that raw numbers cannot. Instead of trying to imagine 13.8 billion years, you imagine January 1st. Instead of trying to feel the weight of 4.6 billion years, you picture early September. Your mind has tools for this. It knows how to move through a year. The magic happens when you begin to translate between cosmic time and calendar time, when you start to feel how much history fits into each familiar unit. In our cosmic year, a single day represents roughly 37 million years of real time. Think about that for a moment. If you woke up on January 2nd of the cosmic year, you would be witnessing nearly 37 million years after the Big Bang. An entire human lifetime, 80 or 90 years, would flash by in about 2 seconds of cosmic time. An hour on the cosmic calendar spans approximately 1.6 million years. The entire span of human civilization, from the first permanent settlements to the present day, would unfold in less than 20 cosmic seconds. The Roman Empire, which felt eternal to those who lived within it, lasted about 3 cosmic seconds. The age of dinosaurs, which dominated Earth for over 160 million years, occupied just 4.5 cosmic days. These translations aren't just mathematical curiosities. They're tools for developing what we might call temporal intuition. When you begin to feel how much real time fits into each calendar unit, you start to develop a sense of proportion that pure numbers can never provide. You begin to understand not just that the universe is old, but how old it is relative to everything you know and care about. This is how you read deep time without going numb. You let the familiar framework of the calendar carry the unfamiliar weight of cosmic history. You don't try to imagine billions of years all at once. Instead, you walk through the year slowly, month by month, week by week, letting the story unfold at a pace your mind can actually follow. You let meaning emerge in layers, like a photograph slowly developing in a dark room. Each cosmic month represents over 1 billion years, but you don't need to hold all billion years in your mind at once. You just need to understand that January was the month of beginning, when the universe was too hot and dense for anything familiar to exist. February was the month of first light, when the cosmic fog finally cleared and space became transparent. March was when gravity began to sculpt the first large structures. April saw the birth of the first galaxies. By walking through the year this way, you build up an intuitive map of cosmic history. You develop landmarks, reference points, a sense of what happened when. The solar system forms in early September. Life appears in late September. Complex cells emerge in November. Animals with backbones show up in mid-December. Each milestone becomes anchored not to an abstract number, but to a moment in the familiar rhythm of the year. But here's the question that emerges as you learn to read this cosmic clock. If human history is truly compressed into those final seconds before midnight, what does that make us? Are we a trivial flicker in a vast story, so brief as to be meaningless? Or are we something rarer and more precious than we ever imagined? The calendar shows us our brevity with ruthless clarity, but brevity alone doesn't determine significance. A lightning flash lasts for milliseconds, but it can illuminate an entire landscape. A single word can change a life. A moment of recognition can reshape how you see everything that came before and everything that might come after. We're going to walk through this cosmic year together, slowly and deliberately, letting the story build the way stories should build. With patience, with attention to detail, with respect for both the vastness of what came before and the remarkable nature of what exists now. We'll discover that learning to read deep time is not about making yourself feel small. It's about learning to see clearly, perhaps for the first time, exactly where you stand in the greatest story ever told. Now we arrive at the moment that stops most people in their tracks, the realization that changes how you see everything that follows. In our cosmic calendar, where the entire history of the universe unfolds across a single year, all of recorded human history occupies only the final seconds of December 31st. Not the final minutes, not the final hour, the final seconds before midnight. Let's be precise about what this means, because precision matters when you're making a claim this extraordinary. When we say recorded history, we're talking about the span of time since humans first began keeping written records, roughly 5,000 years ago. Some civilizations developed writing earlier, others later, but 5,000 years gives us a reasonable estimate for when human beings began documenting their experiences in ways that could be passed down through generations. In cosmic terms, 5,000 years translates to approximately 10 to 15 seconds on our December 31st timeline. Different versions of the cosmic calendar use slightly different scaling factors, so you might hear this described as 10 seconds, 12 seconds, or 15 seconds, but the conclusion remains stable regardless of these small variations. The entire span of human civilization, from the first cuneiform tablets to the device you're using to listen to these words, fits comfortably within the time it takes you to count slowly from 1 to 15. Think about what this compression means in practical terms. The rise and fall of ancient Egypt, one of the longest-lasting civilizations in human history, unfolds in about 2 cosmic seconds. The entire classical period, from the height of Athens to the fall of Rome, occupies roughly 3 seconds. The Middle Ages, the Renaissance, the Age of Exploration, the Industrial Revolution, and the modern era all stack together in the remaining handful of seconds before midnight strikes. But let's go even deeper into this temporal compression, because the more precisely you examine it, the more remarkable it becomes. If we narrow our focus to what we might call modern history, the period since the scientific revolution began in the 1600s, we're looking at roughly 400 years of real time. In cosmic calendar terms, that's less than 1 second. The entire age of modern science, from Galileo's telescope to the Hubble Space Telescope, from Newton's laws to quantum mechanics, from the first steam engines to spacecraft exploring the outer planets, all of it compressed into a single heartbeat of cosmic time. The numbers become even more startling when you consider the pace of recent change. The Industrial Revolution began around 1750, roughly 270 years ago. On the cosmic calendar, that represents about half a second. The age of electricity, automobiles, flight, radio, television, computers, and the internet all unfold within that half-second span. Your grandparents were born in the final tenth of a cosmic second. You were born in the final hundredth of a cosmic second. This is not meant to diminish human achievement or make you feel insignificant. Quite the opposite. This is meant to help you understand something profound about the nature of change, complexity, and consciousness in the universe. For most of cosmic history, change happened slowly. Stars formed over millions of years. Planets cooled over hundreds of millions of years. Evolution shaped new species over millions of years. But in these final seconds of December 31st, the pace of change has accelerated beyond anything the universe had ever seen. Consider what has happened in just the last cosmic second, the last 5,000 years of real time. Humans learned to read and write, transforming our species from one that could only pass knowledge through speech and demonstration to one that could accumulate wisdom across generations. We learned to work metal, to build cities, to navigate by the stars. We developed mathematics sophisticated enough to predict eclipses, philosophy deep enough to question the nature of existence, art beautiful enough to move us to tears thousands of years after its creation. In the last half second, we learned to harness steam, electricity, and the atom itself. We discovered the true age of the Earth, the vast scale of the galaxy, the expansion of the universe. We developed medicines that could cure diseases that had plagued our species for millennia. We built machines that could fly, that could compute, that could see into the depths of space and the interior of atoms. In the last tenth of a second, we learned to split atoms and fuse them, to manipulate DNA, to land on other worlds. We created global communication networks that could connect any 2 points on Earth in milliseconds. We began to understand the quantum nature of reality, the relationship between space and time, the cosmic history that placed us in these final seconds. And in the last 100th of a second, in your lifetime, we've begun to understand artificial intelligence, to sequence entire genomes, to detect gravitational waves from colliding black holes billions of years ago. We've taken the first photographs of the event horizon of a black hole. We've confirmed the existence of thousands of planets orbiting other stars. This is what makes these final seconds so extraordinary. They represent not just the end of the cosmic year, but the moment when the universe became capable of understanding itself. For 13.8 billion years, cosmic history unfolded in darkness, witnessed by no conscious observer capable of grasping its full scope. Stars were born and died, galaxies formed and collided, planets appeared and disappeared, all without any witness who could appreciate the grandeur of what was happening. But now, in these final seconds before midnight, consciousness has emerged. Not just life, which appeared much earlier in the cosmic year, but consciousness capable of looking back across the entire span of cosmic history and understanding it. You are not just living at the end of the cosmic year. You are living at the moment when the cosmic year first became visible to itself. This is the context we need as we explore the deeper story of cosmic time. We are not insignificant specks in a vast, indifferent universe. We are the universe becoming aware of its own magnificent history, and that awareness has emerged only now, only in these precious seconds before midnight. Let's begin our journey through cosmic time at the very beginning, on January 1st of our cosmic calendar. But before we step into that first moment, we need to be clear about what we mean by beginning. This is not the beginning of a myth or a creation story handed down through generations of storytelling. This is the beginning that emerges from evidence, from the careful observation of the universe as it exists today, and the mathematical laws that govern how it changes over time. When cosmologists talk about the Big Bang, they're not describing a moment they witnessed or a story they were told. They're describing the logical conclusion that emerges when you run the movie of cosmic expansion backward. Every galaxy we can observe is moving away from us. The farther away a galaxy is, the faster it's receding. This pattern holds everywhere we look, in every direction, suggesting that space itself is expanding uniformly. If space is expanding now, then it must have been smaller in the past, much smaller. And if you follow this logic far enough backward, you reach a moment when all the matter and energy in the observable universe was compressed into a region smaller than an atom. That moment, 13.8 billion years ago, marks January 1st on our cosmic calendar. not because we know what caused it or what came before it, but because it represents the boundary of our current understanding. Beyond this point, our physics breaks down. Our equations stop working. Time and space themselves become meaningless concepts. We call it the beginning, not because nothing existed before it, but because before is a word that only makes sense after time itself has begun. In those first moments of January 1st, the universe was unlike anything that exists today. The temperature was so high that atoms could not exist. Even protons and neutrons, the building blocks of atomic nuclei, could not hold themselves together. The universe was a seething ocean of fundamental particles and energy, hotter than the core of any star that would ever burn, denser than anything your imagination can grasp. But even in this primordial chaos, laws were at work. The universe was not random. It was not arbitrary. From the very first moments, the cosmos was governed by the same fundamental forces that shape reality today: gravity, electromagnetism, and the nuclear forces that bind particles together or tear them apart. These forces were not imposed on the universe from outside. They were woven into the very fabric of space and time as these dimensions came into existence. As January 1st progressed, as the universe aged from seconds to minutes to hours, something remarkable happened. The cosmic expansion began to cool things down. This cooling was not passive, like a hot cup of coffee gradually reaching room temperature. This was active cooling, driven by the expansion of space itself. As space stretched, the energy contained within it became diluted, spread thinner and thinner across an ever-growing volume. By the end of the first cosmic day, the universe had cooled enough for protons and neutrons to stick together, forming the first atomic nuclei. This was the beginning of chemistry, though chemistry of the simplest kind. Mostly hydrogen, some helium, traces of lithium and beryllium. The periodic table that you learned in school, with its 92 naturally occurring elements, did not yet exist. The universe knew only the lightest elements, the simplest possible combinations of protons and neutrons. But even these simple nuclei could not yet capture electrons to form complete atoms. The universe was still too hot, too energetic. Any electron that tried to settle into orbit around a nucleus would be immediately knocked free by the intense radiation that filled all of space. The cosmos was opaque, filled with a fog of electrically charged particles that scattered light in every direction. You could not have seen across a room in this early universe, let alone across vast distances. Light could travel only tiny distances before being absorbed or scattered. Throughout January, this cosmic fog persisted. The universe continued to expand and cool, but slowly, gradually, like a vast oven cooling after being turned off. The temperature dropped from billions of degrees to millions of degrees to hundreds of thousands of degrees. Still too hot for atoms, still opaque to light, still a universe without stars, without galaxies, without any of the large-scale structures that make the modern cosmos beautiful and complex. This is the first profound lesson of cosmic time. Patience operates on scales that dwarf human understanding. For an entire cosmic month, roughly the first billion years of real time, the universe was content to remain simple. Hot, dense, featureless, but not chaotic. It was following laws, obeying principles, evolving according to rules that would eventually produce galaxies and stars and planets and life itself. Time in this early epoch was not merely a backdrop against which events unfolded. Time was an active ingredient in the cosmic recipe. The expansion of time itself was driving the cooling that would eventually allow atoms to form. The passage of time was diluting the energy density of space, bringing the universe closer to conditions that could support the complex chemistry of stars and planets. Think about what this means for our understanding of time's role in the cosmos. We often think of time as a neutral stage on which the drama of existence plays out. But cosmic time is more than that. It is a creative force, a sculptor that shapes the universe through the simple act of passing. Each moment that ticks by brings new possibilities. Each second of cosmic expansion opens doors that were previously closed. By the end of January on our cosmic calendar, the universe had laid the groundwork for everything that would follow. It had established the fundamental forces, created the lightest elements, and cooled to the point where atoms would soon be possible. It had not yet produced a single star, but it had created the conditions that would make stars inevitable. The cosmic stage was set. The elements were in place. The laws were established. And time itself was ready to begin its long work of transformation, turning simplicity into complexity, turning chaos into cosmos, turning a hot, dense beginning into a universe capable of hosting galaxies, planets, life, and consciousness. As we move into February of our cosmic calendar, something extraordinary happens that transforms the universe forever, though it happens so quietly that if you had been there, you might have missed it entirely. After nearly 400,000 years of cosmic time, after an entire month of expansion and cooling, the universe finally reaches a temperature cool enough for electrons to settle into stable orbits around atomic nuclei. For the first time since the beginning, complete atoms can exist without being immediately torn apart by radiation. This moment, roughly 400,000 years after the Big Bang, marks one of the most important transitions in cosmic history. Suddenly, the fog that had made the universe opaque begins to clear. The electrically charged particles that had been scattering light in every direction combine into neutral atoms that barely interact with photons at all. Light, which had been trapped in an endless game of pinball, bouncing from particle to particle in random directions, suddenly finds itself free to travel across vast distances unimpeded. In that moment, the universe becomes transparent. Space, which had been filled with an impenetrable glare, suddenly becomes clear and dark. This is the cosmic equivalent of fog lifting from a landscape, revealing mountains and valleys that were always there but had been hidden from view. Except in this case, what becomes visible is not landscape, but the infinite depth of space itself, stretching away in all directions, ready to be filled with the structures that will define the cosmos for billions of years to come. But something else happens in this moment of clearing, something that turns the early universe into a kind of cosmic time capsule. The light that becomes free to travel when the fog lifts doesn't just disappear into the void. It carries with it a perfect record of what the universe looked like at that moment of transition. Every photon that escapes capture becomes a messenger, encoding information about the temperature, density, and conditions that existed when space first became transparent. This ancient light still surrounds us today. We call it the cosmic microwave background radiation, and it represents the oldest light in the universe, the first light that was ever free to travel across cosmic distances. When you tune a radio between stations and hear that faint static, about 1% of that noise is the echo of this primordial glow, the stretched and cooled remnant of the moment when the universe first became clear. Think about what this means. Every direction you look in space, you can see back to this moment of first light. The universe has become a museum of its own history, with the most ancient exhibits displayed on the most distant walls. Space itself serves as an archive, preserving evidence of cosmic conditions from billions of years ago in the form of light that has been travelling toward us ever since the fog first lifted. This is one of the most beautiful concepts in all of cosmology, that looking out into space is equivalent to looking back in time. The light from nearby stars left those stars years ago. Light from distant galaxies left those galaxies millions or billions of years ago. and the cosmic microwave background carries information from the very moment when the universe first became transparent, nearly 14 billion years ago. The deeper we look into space, the further back in time we see. But after this moment of cosmic clearing, after this transition from opacity to transparency, something remarkable happens in terms of the pace of cosmic change. Almost nothing happens for a very long time. This is the beginning of what cosmologists sometimes call the cosmic dark ages, a period that lasts for hundreds of millions of years, during which the universe remains dark, quiet, and seemingly inactive. No stars yet shine, no galaxies yet spiral through space. The universe has expanded and cooled to the point where it consists mostly of neutral hydrogen and helium gas, spread almost uniformly throughout space, with only the tiniest variations in density from one region to another. From our perspective, accustomed to the drama of stellar birth and death, of galactic collisions and exploding supernovae, this period might seem boring, uneventful, a cosmic intermission between the excitement of the Big Bang and the fireworks of star formation. But this apparent quiet conceals a profound preparation. During these hundreds of millions of years, gravity is working patiently and persistently on those tiny variations in gas density. Regions that are slightly denser than average begin to attract more matter. Regions that are slightly less dense begin to lose matter to their denser neighbours. Slowly, imperceptibly, the nearly uniform distribution of matter begins to develop structure. This is cosmic patience operating on a scale that human minds struggle to comprehend. For a period of time longer than the Earth has existed, longer than multicellular life has existed, longer than complex cells have existed, the universe appears to be doing nothing more than getting slowly more clumpy. But this slow clumping is laying the foundation for everything that will make the cosmos interesting: galaxies, stars, planets, chemistry, and eventually life itself. The cosmic dark ages teach us something essential about how complexity emerges in nature. The most dramatic transformations often require long periods of apparent inactivity, during which invisible forces are slowly building the conditions that will make rapid change possible. The universe is learning, during these quiet centuries of millions of years, how to concentrate matter, how to build the gravitational wells that will eventually become the sites of star formation and galaxy assembly. For a while, almost nothing happens, except that everything that matters later is being made possible. The universe is not in a hurry. It has no schedule to keep, no deadlines to meet. It can afford to spend hundreds of millions of years just letting gravity do its slow work of organization and concentration. Time is long, so long that it can afford experiments, false starts, and gradual adjustments. This cosmic patience will become a recurring theme as we move through our year-long journey. Again and again, we will see the universe taking its time, building foundations slowly and carefully before attempting the more complex construction projects that will eventually populate space with stars and planets and the conditions necessary for life. The first light and the long quiet that follows remind us that the cosmos operates on timescales that make human patience seem like frantic urgency, and that the most profound changes often require the longest preparations. As we move into the spring months of our cosmic calendar, March and April and May, something beautiful begins to happen in the darkness. The tiny variations in density that gravity has been working on so patiently during the cosmic dark ages finally reach a critical threshold. What started as imperceptible differences in the distribution of matter, variations so small they would have been invisible to any observer, begin to grow into the first large-scale structures the universe has ever seen. Gravity, you see, is the universe's most patient artist. It works slowly, steadily, without drama or fanfare, but with absolute persistence. Unlike the other fundamental forces which can push things apart or hold them together over short distances, gravity only pulls. And it pulls on everything that has mass or energy. It never gets tired, never stops working, never gives up on its long-term projects. During these spring months of cosmic time, representing hundreds of millions of years, gravity begins to sculpt the cosmos into something recognizable. The nearly uniform sea of hydrogen and helium gas that filled space begins to develop currents and eddies, streams and pools. Matter flows along invisible pathways carved by gravitational attraction, following routes determined by the subtle density variations that emerged in the universe's first moments. Think of gravity as a cosmic gardener, working on the largest possible scale. Just as a gardener might gradually reshape a landscape over decades, moving soil, redirecting water flow, encouraging growth in some areas while clearing others, gravity reshapes the distribution of matter throughout the universe. But gravity's garden project takes not decades, but hundreds of millions of years, and the materials it works with are not soil and water, but vast clouds of primordial gas scattered across billions of light-years of space. The first structures to emerge from this gravitational sculpting are not yet the galaxies we see today, but rather the cosmic scaffolding on which galaxies will eventually be built. Vast filaments of dark matter, invisible to our eyes but detectable through its gravitational influence, begin to form a web-like structure throughout space. These dark matter filaments serve as gravitational highways, channels along which ordinary matter will flow to collect in the densest regions. Where these cosmic filaments intersect, where multiple streams of matter converge, the first galactic nurseries begin to take shape. These regions become gravitational wells, cosmic valleys into which surrounding matter naturally falls. As more and more material accumulates in these valleys, the gravitational pull becomes stronger, attracting matter from ever greater distances in a process that feeds on itself. This is how the first galaxies are born, not through sudden explosive events, but through the patient accumulation of material over vast periods of time. Gravity gathers the raw ingredients, concentrates them in particular regions of space, and gradually builds up the dense collections of matter that will eventually become the stellar cities we call galaxies. But here's what makes this process so remarkable. Each galaxy becomes, in effect, a time machine. Because light travels at a finite speed, when you look at a distant galaxy, you're seeing it as it was when that light first began its journey toward your eyes. The most distant galaxies we can observe appear to us as they were when the universe was young, when they were just beginning to form. Closer galaxies show us later stages of galactic evolution. Our own galactic neighborhood reveals the most recent chapter in this ongoing story of cosmic structure formation. This means that by studying galaxies at different distances, astronomers can observe the entire history of galaxy formation spread out across space. It's as if the universe has arranged itself as a living textbook, with the oldest chapters written on the most distant pages and the newest chapters close at hand. Space itself becomes a library of cosmic evolution, preserving examples of every stage of galactic development for us to study and understand. Gravity, in this sense, is teaching the universe how to keep a diary. Each galaxy that forms becomes a record of the conditions that existed when and where it came together. The size of a galaxy tells us about the strength of gravity in its region of space. The age of its stars reveals when it first began converting gas into luminous matter. The chemical composition of those stars records the history of stellar birth, death, and rebirth that has occurred within that galactic system. As spring progresses into summer on our cosmic calendar, this process of gravitational gathering accelerates. The first galaxies begin to light up as their accumulated gas reaches sufficient density to ignite the first generation of stars. These early galaxies are different from the ones we see today, smaller, more chaotic, filled with massive young stars that burn bright and die fast, but they represent the universe's first successful experiments in large-scale organization, the first time that gravity has managed to collect enough matter in one place to create something genuinely complex and dynamic. The formation of the first galaxies marks a fundamental transition in cosmic history. For the first time since the Big Bang, the universe begins to develop distinct neighborhoods, regions of space with their own character and history. No longer is space filled with a nearly uniform distribution of matter. Now it has structure, architecture, a cosmic cityscape of gravitational communities separated by vast stretches of nearly empty space. This galactic architecture will persist for the rest of cosmic history. Once established, these gravitational wells will continue to grow and evolve, capturing new material, spawning new generations of stars, sometimes merging with neighboring galaxies to create even larger structures. The cosmic web that begins to emerge in the spring months of our calendar will serve as the framework on which all subsequent cosmic evolution takes place. Gravity has learned during these patient months of accumulation and organization how to transform the simple into the complex, how to turn uniformity into diversity, how to create islands of intense activity within an ocean of relative emptiness. The universe is beginning to write its autobiography, one galaxy at a time, and that autobiography will continue to be written for billions of years to come. As summer arrives on our cosmic calendar, the universe finally begins to shine. After hundreds of millions of years of darkness, after patient months of gravitational gathering and galactic assembly, conditions are finally right for the most transformative event in cosmic history, the birth of the first stars. These ancient suns, massive beyond anything we see in today's sky, ignite the cosmic dark ages and begin the long process of turning a simple universe into a chemically complex one. But stars are much more than sources of light and warmth. They are the universe's great alchemists, cosmic furnaces that take the simple ingredients left over from the Big Bang and forge them into something far richer and more complex. The early universe knew only hydrogen and helium, with traces of lithium and beryllium. Everything else on the periodic table, every element essential to planets and life, and the rich chemistry of existence, had to be created inside the nuclear fires of stellar cores. Think about what this means for your own existence. The carbon in your cells, the oxygen you breathe, the iron in your blood, the calcium in your bones. None of these elements existed when the universe was young. They had to be manufactured, atom by atom, inside stars that lived and died billions of years before the solar system was even a possibility. Every heavy element in your body is the product of nuclear reactions that took place in stellar cores under conditions of temperature and pressure so extreme that they turn science fiction into routine stellar physics. This is how stars work their alchemy. In the crushing heat and pressure of stellar cores, temperatures reach tens of millions of degrees, hot enough to overcome the electrical repulsion between atomic nuclei and force them to fuse together. Hydrogen nuclei combine to form helium, releasing tremendous amounts of energy in the process. This energy works its way slowly to the stellar surface, taking thousands of years to complete the journey, and then radiates into space as the light and heat we associate with stars. But stellar nucleosynthesis doesn't stop with helium. As a star ages and its core temperature rises, it begins fusing helium into carbon, carbon into oxygen, oxygen into silicon, and silicon into iron. Each successive fusion reaction requires higher temperatures and pressures, pushing stellar cores to ever more extreme conditions. The most massive stars can build elements all the way up to iron, creating a cosmic periodic table that grows more complex with each stellar generation. The first stars of summer, those massive pioneers that ended the cosmic dark ages, were different from the stars we see today. Built from the pure hydrogen and helium of the early universe, they burned hot and fast, living only a few million years before exhausting their nuclear fuel. But their brief lives had consequences that would echo throughout cosmic history. When these stellar giants died, they didn't fade quietly into darkness. They exploded as supernovae, the most violent and luminous events the universe had yet seen. These supernova explosions did something that would prove essential to everything that followed. They scattered the heavy elements forged in stellar cores throughout the surrounding space. Carbon, oxygen, silicon, iron, and dozens of other elements that had been locked away in stellar interiors were suddenly freed, mixing with the primordial hydrogen and helium to create the first chemically enriched regions of the galaxy. This process of stellar death and chemical enrichment established a cosmic cycle that continues to this day. Each generation of stars builds on the chemical legacy of the previous generation, incorporating heavier elements into new stellar systems and creating conditions for even more complex chemistry. The universe learns through this process how to become progressively more interesting, more diverse, more capable of supporting complex structures and eventually life itself. You are a direct beneficiary of this stellar inheritance. The atoms that make up your body have been through multiple cycles of stellar birth, life, and death. The carbon that forms the backbone of every organic molecule in your cells was forged in the core of a star that died billions of years ago. The oxygen you breathe with every breath was created in stellar fires and scattered into space by supernova explosions. The iron that carries oxygen in your bloodstream was manufactured under conditions that exist nowhere else in the universe except in the hearts of dying stars. This is not merely a poetic metaphor. This is literal truth, confirmed by decades of research into stellar evolution and nuclear physics. You are made of star stuff in the most direct and concrete sense possible. The elements essential to your existence could not have been created in any other way. The universe had to build and destroy countless generations of stars before it could produce the chemical complexity necessary for planets like Earth and life like yours to exist. This realization transforms how we understand our place in the cosmic calendar. Yes, we are recent arrivals, appearing only in the final seconds of December 31st. But we are not strangers to the cosmic story. We are its direct descendants, built from materials that have been in the making since the first stars began to shine. Our chemical heritage stretches back through summer and spring to the very foundations of cosmic structure. The cosmic calendar is not only about smallness, about the brief span of human existence compared to the vast age of the universe. It is also about inheritance, about the deep connections that link us to every stage of cosmic evolution. We carry within our bodies the nuclear signatures of stellar processes that took place billions of years before the Earth existed. We are walking libraries of cosmic history, living repositories of stellar evolution, embodied evidence of the universe's long journey from simplicity to complexity. Stars, in this sense, are the universe's foundries of meaning. They take the raw materials left over from the Big Bang and transform them into the ingredients necessary for planets, chemistry, and life. They are the bridge between the simple early universe and the complex modern cosmos. Without stellar nucleosynthesis, the universe would remain forever simple, forever limited to the lightest elements, forever incapable of producing the rich chemical tapestry that makes planets and life possible. As summer progresses on our cosmic calendar, more and more stars ignite, each one adding its contribution to the growing chemical complexity of the cosmos. The universe is learning, star by star, how to build the periodic table, how to create the elemental diversity that will eventually make our own existence possible. We have travelled through cosmic spring and summer, watching gravity sculpt the first galaxies and stars, forge the heavy elements that make complex chemistry possible. Now, as early September arrives on our cosmic calendar, something remarkable happens in one particular corner of one particular galaxy. A cloud of gas and dust begins to collapse under its own gravity, and from this collapse our solar system is born. This moment, 4.6 billion years ago in real time, represents early September on our compressed timeline. Think about what this means for perspective. The universe has already been in existence for over 9 billion years by the time our sun begins to shine. Galaxies have been forming and evolving for cosmic months. Multiple generations of stars have lived and died, enriching space with heavy elements. The cosmic web of dark matter and ordinary matter has long since established the large-scale architecture of the universe. And only now, only in early September of the cosmic year, does our local star system finally make its appearance. Earth is not ancient by cosmic standards. Our planet is not an elder statesman among the worlds of the universe. We are latecomers to the cosmic story, residents of a solar system that formed in the universe's middle age, long after the first galaxies had established their mature structures and settled into their long-term evolutionary patterns. If the universe were a vast city, Earth would be a building constructed in a neighborhood that had already been established, developed, and populated for eons. But this lateness turns out to be crucial to our existence. The solar system could not have formed much earlier than early September, because the universe needed time to prepare the materials from which planets are made. The carbon, oxygen, silicon, and iron that make up rocky planets like Earth had to be manufactured inside multiple generations of stars and then scattered into space by supernova explosions. The heavy elements that form the solid foundations of terrestrial worlds were not available in the early universe. They had to be created, distributed, and incorporated into new stellar systems over billions of years of cosmic evolution. The formation of the solar system follows a process that has been repeated countless times throughout the galaxy, but each instance is unique in its details. Our story begins with a vast molecular cloud, a region of space where gas and dust have accumulated over millions of years. This cloud, hundreds of times larger than our current solar system, drifts through the galaxy for eons, slowly rotating, gradually condensing under the weak but persistent pull of its own gravity. Something triggers the final collapse of this cloud. Perhaps a nearby supernova explosion sends shockwaves through the region, compressing the gas and dust beyond the point where it can resist its own gravitational attraction. Perhaps the gravitational influence of a passing star or the spiral arms of the galaxy itself provides the necessary push. The exact trigger may never be known, but the result is clear. The cloud begins to contract rapidly, spinning faster as it shrinks, like a figure skater pulling in her arms. As the cloud collapses, most of the material falls toward the center, where it accumulates into a dense, hot core that will eventually become our sun. But not all the material makes it to the center. The rotation of the collapsing cloud causes some of the gas and dust to settle into a disk around the forming star, a vast rotating pancake of matter from which the planets will eventually condense. This is where Earth's story truly begins, not with a single moment of formation, but with a gradual process of accretion that takes tens of millions of years to complete. In the inner regions of the solar disk, where temperatures are high enough to vaporize water and most organic compounds, only rocky and metallic materials can condense into solid form. Tiny grains of dust stick together through electrostatic forces, building up larger and larger aggregates. These aggregates collide and merge, sometimes gently, sometimes violently, gradually sweeping up more and more material from their orbital neighborhoods. Earth grows through this process of collision and accumulation, starting as a collection of dust grains and ending up as a planet massive enough to hold onto an atmosphere and reshape its own surface through geological processes. The early Earth is a violent place, constantly bombarded by asteroids and comets, its surface molten from the heat of impact and radioactive decay. But gradually, as the bombardment decreases and the planet cools, something extraordinary begins to happen. Earth becomes a laboratory for chemistry unlike anything the universe has seen before. While stars excel at nuclear chemistry, fusing light elements into heavier ones under extreme conditions of temperature and pressure, planets excel at what we might call gentle chemistry, the complex molecular interactions that take place at moderate temperatures in the presence of liquid water and solid surfaces. This is the crucial transition that happens in early September of our cosmic calendar. For the first time in cosmic history, the universe has produced a world where water can exist in liquid form, where complex molecules can form and persist, where chemical reactions can proceed slowly and selectively rather than being driven by the overwhelming energy of stellar cores. Earth becomes the first place in our corner of the galaxy where chemistry can truly experiment, where molecules can become large and complex without being immediately destroyed by radiation or extreme heat. Once Earth arrives, the cosmic story begins to accelerate in ways that would have been impossible earlier. The patient processes of stellar evolution and galactic development, which operate on timescales of millions and billions of years, give way to the faster rhythms of planetary geology, atmospheric evolution, and eventually biological change. Chemistry finds a new stage, and on that stage it will soon begin composing the most complex and beautiful compositions in the known universe. Earth is not just another planet in the cosmic catalogue. It is a world that arrives at precisely the right moment in cosmic history, when the universe has finally accumulated enough chemical complexity to support the intricate molecular processes that will, in the cosmic months to come, give rise to life itself. As we move through October and November of our cosmic calendar, Earth begins the long, patient work of learning its own chemistry. The violent bombardment that characterized the planet's early formation gradually subsides, and for the first time in its brief history, Earth has the opportunity to develop stable, persistent systems. This is when our planet transforms from a collection of rocky debris into something genuinely planetary, a world with an atmosphere, oceans, and the complex cycles that will define its character for billions of years to come. The Earth of October and November is almost unrecognizable compared to the world you know today. The atmosphere is a toxic mixture of methane, ammonia, hydrogen, and water vapor with virtually no free oxygen. The surface is still scarred by massive impact craters, and volcanic activity reshapes the landscape on a scale that dwarfs anything in recorded human history. The oceans, when they finally form, are more like a hot mineral-rich soup than the clear blue waters that will eventually support marine life. Yet even in this alien environment, Earth is beginning to demonstrate something that sets it apart from every other world we know: the ability to maintain complex, interconnected systems that persist and evolve over geological time. Water plays a central role in this planetary transformation. As Earth cools below the boiling point of water, something remarkable happens for the first time in our corner of the solar system. Water vapor in the atmosphere begins to condense and fall as rain. Not just occasional showers, but torrential downpours that may have lasted for millions of years, gradually filling the low-lying areas of the planet's surface with the first primitive oceans. These early seas are nothing like the oceans of today, saturated with dissolved minerals, heated by volcanic vents, and stirred by tidal forces far stronger than anything we experience now. But they represent something new in the cosmic story: stable reservoirs of liquid water persisting on a planetary surface. The formation of stable oceans marks the beginning of Earth's first great lesson in planetary chemistry: the water cycle. Water evaporates from the ocean surface, rises into the atmosphere, condenses into clouds, and falls again as precipitation. This seems simple, almost mundane from our modern perspective, but it represents a profound innovation in cosmic chemistry. For the first time, the same molecules are cycling repeatedly between different physical states and different locations, creating a dynamic system that can transport materials, moderate temperatures, and create complex chemical gradients across the planet's surface. But Earth's chemical education extends far beyond the water cycle. The planet begins to develop what we now recognize as the first version of the carbon cycle. As atmospheric carbon dioxide dissolves in seawater, reacts with minerals on the ocean floor, and is eventually recycled back to the atmosphere through volcanic outgassing. The nitrogen cycle begins as lightning fixes atmospheric nitrogen into forms that can dissolve in water and participate in more complex chemical reactions. Even the oxygen cycle has its primitive beginnings, though it will be billions of years before oxygen becomes a major component of the atmosphere. These cycles represent something unprecedented in the cosmic story up to this point. While stars operate as fusion reactors, converting simple elements into complex ones through nuclear processes, and while space provides a vast laboratory for simple chemical reactions, Earth becomes something entirely new. A planetary-scale chemical reactor where the same materials can be recycled, recombined, and transformed through countless different pathways over enormous periods of time. Time is long, so long it can afford experiments. This becomes Earth's governing principle during these cosmic months of October and November. The planet has no deadline to meet, no rush to achieve particular results. It can try different chemical combinations, different atmospheric compositions, different ocean chemistries. It can experiment with volcanic cycles, with the gradual drift of continents, with the slow evolution of atmospheric composition. Each experiment lasts millions of years, long enough to explore all the possible consequences and interactions. This is where Earth begins to develop what we might call planetary intelligence, not consciousness in any biological sense, but rather the capacity for complex self-regulation that emerges from the interaction of multiple interconnected systems. The planet learns to moderate its own temperature through the greenhouse effect, adjusting the concentration of atmospheric gases to maintain liquid water even as the sun's brightness slowly increases over geological time. It learns to recycle essential elements like carbon and nitrogen, preventing them from being permanently locked away in rocks or lost to space. It develops feedback mechanisms that help maintain stability even as individual components change. The concept of planetary intelligence might seem like a metaphor, but it points towards something real and important about how Earth operates. The planet's various systems, atmosphere, oceans, geology, and eventually biology don't just coexist independently. They influence each other in ways that tend to maintain conditions suitable for continued complexity. Earth becomes a self-regulating system, not through conscious design, but through billions of years of trial and error, of chemical experimentation, of gradual refinement of the processes that govern planetary behavior. During these months of chemical learning, Earth also begins to develop the infrastructure that will eventually support life. The planet's magnetic field stabilizes, protecting the atmosphere from being stripped away by solar wind. The continental landmasses begin to take shape as plate tectonics gets underway, creating the geological diversity that will provide different environments for future biological experiments. The atmosphere gradually shifts toward a composition that, while still toxic to most forms of life we recognize today, contains the chemical ingredients necessary for the more complex molecular processes that will soon emerge. By the end of November on our cosmic calendar, Earth has transformed itself from a chaotic collection of rock and gas into something approaching the stable, chemically complex world that could potentially support life. The planet has learned the basics of atmospheric chemistry, ocean chemistry, and geological cycling. It has developed the capacity for chemical self-regulation and long-term stability. Most importantly, it has created conditions where chemistry can operate slowly and selectively, where complex molecules can form and persist, where the next great chapter in the cosmic story can finally begin to unfold. Earth has become a world that is ready for life, even if life itself has not yet appeared. As we approach the end of November and the beginning of December on our cosmic calendar, somewhere in Earth's primitive oceans, something extraordinary happens. It happens so quietly, so gradually, that if you could travel back in time to witness it, you might not recognize its significance. There are no explosions, no dramatic transformations, no sudden illumination of the landscape. Instead, in the warm, mineral-rich waters near volcanic vents or in shallow tidal pools where chemistry has been experimenting for millions of years, certain collections of molecules begin to do something that has never happened before in the history of the universe. They begin to maintain themselves. This is how life appears on our planet, not as a single moment of creation, but as a gradual transition from complex chemistry to self-maintaining chemistry. The boundary between living and non-living is not a sharp line, but rather a blurry region where certain molecular systems become capable of preserving their own structure, repairing damage, and most remarkably, making copies of themselves that can persist even after the original systems break down. When scientists talk about life, they're describing a very specific set of capabilities that certain chemical systems can develop. Life, at its most fundamental level, is chemistry that has learned to manage information. Living systems can store instructions for building and maintaining themselves. They can read those instructions and follow them with reasonable accuracy, and they can pass copies of those instructions on to the next generation. This is what distinguishes a living cell from even the most complex non-living chemical reaction: the ability to encode, process, and transmit the information necessary for self-maintenance and reproduction. The first life forms to appear in Earth's oceans are almost unimaginably simple compared to any organism you're familiar with today. They are single cells without nuclei, without specialized internal structures, without any of the sophisticated molecular machinery that characterizes modern bacteria. Yet even these primitive cells represent one of the most profound innovations in cosmic history: the emergence of chemistry that can direct its own future, that can actively work to preserve and propagate itself, rather than simply following the passive laws of physics and chemistry. These early microorganisms, appearing in late November of our cosmic year, begin immediately to reshape their planetary environment in ways that will have consequences lasting billions of years. They don't just live on Earth, they begin to live with Earth, entering into chemical relationships with the atmosphere, oceans, and rocks that will gradually transform the entire planetary system. Life and environment become partners in a dance that continues to this day. The most significant thing about early life is not its complexity, but its persistence and its patience. For the next 1.5 billion years of real time, representing most of December on our cosmic calendar, life remains almost exclusively microbial. There are no plants, no animals, no forests or coral reefs. The biosphere consists entirely of single-celled organisms, most of them invisible to the naked eye, living in the oceans and gradually spreading to every corner of the planet where liquid water exists. This microbial dominance is not a period of stagnation or failed evolution. It is a time of the most fundamental biological innovation the planet has ever seen. These invisible organisms invent photosynthesis, the process of capturing sunlight and using its energy to build complex molecules from simple ingredients. They develop the biochemical pathways that will eventually power all life on Earth. They learn to extract energy from chemical reactions that had never been exploited before, opening up new possibilities for life in environments that had previously seemed sterile. Most importantly, these early microorganisms begin the slow process of terraforming their own planet. Photosynthetic bacteria begin to release oxygen as a waste product, gradually changing the composition of Earth's atmosphere. This oxygen revolution, unfolding over hundreds of millions of years, represents one of the most dramatic environmental transformations in planetary history. The early atmosphere, dominated by methane and other reducing gases, gives way to an oxygen-rich atmosphere that will eventually support the complex multicellular life forms of the future. But this transformation is not rapid or dramatic. It requires cosmic patience on a scale that makes human patience seem like frantic urgency. For most of the life story, most of Earth's biological history, the planet belongs to microorganisms. They are the pioneers, the inventors, the planetary engineers who slowly but systematically prepare the world for the more complex forms of life that will eventually follow. This microbial dominance teaches us something profound about the nature of evolutionary time. The most fundamental innovations in the history of life, the basic biochemical processes that still power every living thing on Earth, were developed during this long period of apparent simplicity. While the visible world remained unchanged, while Earth's surface showed no obvious signs of biological activity, invisible organisms were conducting the most important research and development project in planetary history. They learned how to harness the energy of sunlight, how to build complex molecules from atmospheric carbon dioxide, how to extract nutrients from rocks and seawater, how to survive in extreme environments, how to cooperate with other microorganisms in ways that benefit all participants. These innovations, developed over billions of years of microbial evolution, would eventually make possible everything from towering forests to thinking brains. Life appears quietly because life begins quietly. It does not announce itself with fanfare or demand immediate recognition. Instead, it starts as a subtle enhancement to chemistry, a gentle elaboration of processes that were already occurring in the non-living world. But once life appears, once chemistry learns to manage information and direct its own development, the trajectory of planetary evolution changes forever. Earth now has something it never had before: a biosphere, a living layer that will gradually spread across every available surface, that will learn to shape its own environment, and that will eventually develop the capacity for consciousness, intelligence, and the ability to understand its own cosmic context. Life appears quietly in late November, but its appearance marks the beginning of the most remarkable chapter in Earth's 4 billion-year story. As we move into mid-December of our cosmic calendar, life on Earth begins one of its most profound experiments in cooperation. After more than 1 billion years of exclusively microbial existence, after eons of single-celled organisms perfecting the basic biochemistry of life, something remarkable happens that will transform not just biology, but the entire future trajectory of evolution on our planet. Life begins to discover the power of partnership, the revolutionary idea that sometimes survival favors not the strongest individual, but the beings that can learn to share. The first great breakthrough in biological complexity comes with the invention of the eukaryotic cell, a cell with a nucleus and specialized internal structures called organelles. This might seem like a minor technical innovation, a small step in the gradual progression from simple to complex life forms. But the emergence of eukaryotic cells represents something far more profound. The first time in Earth's history that separate living systems learn to live as one, creating something new and more capable than either partner could achieve alone. The story of how eukaryotic cells emerged is one of the most beautiful examples of cooperation in all of biology. Billions of years ago, certain bacteria developed the ability to use oxygen to extract energy from food molecules far more efficiently than had ever been possible before. Meanwhile, other bacteria became experts at photosynthesis, capturing sunlight and converting carbon dioxide into organic compounds. These different bacterial lineages had each solved different pieces of the energy puzzle, but they remained separate, independent organisms competing for resources in the same environment. Then something unprecedented happened. Instead of competing to extinction, some of these bacteria began to live inside other cells, forming partnerships that benefited everyone involved. The bacteria that were good at using oxygen became the mitochondria, the cellular powerhouses that still generate energy in every complex cell on Earth, including the cells in your own body. The bacteria that were good at photosynthesis became the chloroplasts that power plant cells and ultimately sustain nearly all life on our planet. This process, which scientists call endosymbiosis, represents a fundamental shift in how evolution works. For the first 1.5 billion years of life on Earth, evolutionary innovation came primarily through competition, through random mutations that occasionally gave one organism an advantage over its rivals. But with endosymbiosis, evolution discovered partnership. It learned that sometimes the most effective way to solve complex problems is not to outcompete your neighbors, but to invite them to become part of your family. The eukaryotic cell that emerged from these ancient partnerships became the foundation for all complex life on Earth. Every plant, animal, and fungus that has ever existed is built from eukaryotic cells that still contain the bacterial partners that joined the alliance billions of years ago. The mitochondria in your muscle cells are the direct descendants of bacteria that chose cooperation over competition in the deep waters of ancient oceans. When you take a breath, you're benefiting from a partnership that was forged when life first learned that survival sometimes favors the beings that can share. But the invention of complex cells was only the beginning. The next great innovation in biological cooperation came with the emergence of multicellular life, organisms built not from a single cell, but from communities of cells working together toward common goals. This transition, which began in mid-December of our cosmic year, required life to solve an entirely new set of problems. How do individual cells coordinate their activities? How do they communicate with each other? How do they specialize in different functions while remaining part of a unified organism? The first multicellular organisms were simple affairs, loose collections of similar cells that could coordinate basic activities like movement and feeding. But over time, these cellular communities became increasingly sophisticated. Cells began to specialize, with some becoming experts at capturing sunlight, others at digesting food, still others at reproduction or defense. These specialized cells became increasingly dependent on each other, creating organisms that were genuinely more than the sum of their parts. This cellular cooperation set the stage for all the biological complexity that would follow. The towering trees that would eventually cover Earth's continents are communities of billions of specialized cells working together. The animals that would populate land and sea are walking, swimming examples of cellular cooperation on an almost unimaginable scale. Your own body contains roughly 37 trillion cells, each one descended from bacteria that learn to cooperate rather than compete, all of them working together to maintain the complex biological system that enables your consciousness, your thoughts, and your ability to contemplate your place in cosmic history. The emergence of multicellular life in mid-December also began the process that would eventually lead to ecosystems, to complex webs of interaction between different species. If individual cells could learn to cooperate to form organisms, perhaps organisms could learn to cooperate to form even larger, more complex systems. Plants would eventually learn to depend on animals for seed dispersal and pollination. Animals would learn to depend on plants for food and oxygen. Entire forests would emerge as cooperative networks where trees share nutrients through underground fungal connections, where the survival of individual organisms becomes intimately connected to the health of the whole system. This theme of cooperation as a driving force in evolution offers a gentle but profound insight for anyone contemplating their place in the cosmic story. The most successful innovations in the history of life have often involved not conquest but partnership, not domination but mutually beneficial relationships that allow all participants to thrive. The bacteria that became mitochondria didn't surrender their identity when they joined larger cells. They found a way to maintain their essential functions while contributing to something greater than themselves. Perhaps this pattern, first established in the deep waters of ancient Earth, continues to influence evolution even today. Perhaps in the long run, survival favors not the individuals who can dominate their environment, but the beings that can learn to share it, that can find ways to contribute to the larger systems that sustain all life. The slow invention of complexity, unfolding over hundreds of millions of years in mid-December of our cosmic year, suggests that cooperation may be not just a nice ideal, but a fundamental principle of how complexity emerges in the universe. On Christmas Day of our cosmic calendar, something magnificent happens that will help you hold on to the true scale of deep time for the rest of your life. As December 25th dawns in our compressed timeline, the first dinosaurs appear on Earth. This timestamp, Christmas Day, becomes one of the most memorable reference points in the entire cosmic year, a moment you can return to whenever you need to grasp the relationship between human perception and cosmic reality. Think about what December 25th represents in your own experience of time. Christmas Day carries emotional weight, cultural significance, a sense of specialness that makes it stand out from all the ordinary days of the year. It's a date that feels important, memorable, anchored in your personal and collective consciousness. Now imagine that this same date, December 25th, marks the beginning of one of the most spectacular chapters in Earth's biological history, the rise of the dinosaurs. The dinosaurs first appear roughly 230 million years ago in real time, which translates to Christmas Day on our cosmic calendar. But here's what makes this timestamp so powerful for understanding deep time. The entire age of dinosaurs, from their first appearance to their final extinction, occupies only the last week of the cosmic year. The reign of the dinosaurs, which feels almost incomprehensibly vast from our human perspective, fits comfortably between December 25th and December 30th. Let's pause to feel the weight of this compression. When you think about dinosaurs, you're thinking about creatures that dominated Earth for over 160 million years. This is a span of time so long that it challenges your ability to comprehend it. The Stegosaurus lived closer in time to you than it did to Tyrannosaurus rex. The gap between the early Jurassic and the late Cretaceous periods represents more time than has passed since complex life first appeared on land. From a human perspective, the age of dinosaurs seems to stretch back almost to the beginning of time itself. But on the cosmic calendar, this vast age of dinosaurian dominance occupies just 6 days. 6 days out of 365. The creatures that seem to rule Earth forever, that established ecosystems of breathtaking complexity, that evolved into forms ranging from hummingbird-sized hunters to long-necked giants taller than trees, did all of this in less than 2% of cosmic time. The entire age of dinosaurs, from Christmas Day to December 30th, represents a brief experiment in one particular approach to large-scale multicellular life. This perspective offers a profound lesson about the nature of dominance itself. From within the age of dinosaurs, if you had been a conscious observer during the Jurassic or Cretaceous periods, dinosaurian dominance would have seemed permanent, eternal, the natural order of things. For millions of generations, these creatures shaped the terrestrial biosphere, filled every available ecological niche, dominated land, sea, and sky. They were so successful, so diverse, so perfectly adapted to their world that it would have been impossible to imagine Earth without them. Yet even this spectacular success was temporary when viewed on the cosmic timescale. The dinosaurs, for all their diversity and dominance, were a 6-day phenomenon in the cosmic year. They rose, flourished, diversified, and disappeared within a single week of cosmic time. Their reign, which seemed eternal from within its own context, was just one brief chapter in the much longer story of Earth's biological evolution. This is not meant to diminish the achievements of dinosaurs or to suggest that their dominance was somehow insignificant. The dinosaurs were magnificent creatures that pushed the boundaries of what was possible in terms of size, diversity, and ecological complexity. They established evolutionary patterns that continue to influence life on Earth today. Birds, which are direct descendants of dinosaurs, still populate our skies and remind us that dinosaurian lineages never completely disappeared. The age of dinosaurs was a time of spectacular biological innovation and success. But the cosmic calendar teaches us to hold even spectacular success lightly, to recognize that dominance, no matter how complete it appears from within its own time frame, is always temporary when viewed from the perspective of deep time. The lesson is both humbling and oddly comforting. Even the most successful adaptations, the most complete conquest of available ecological niches, the most seemingly permanent arrangements of power and dominance, are ultimately brief experiments in the longer story of cosmic evolution. The Christmas Day timestamp helps you internalize this perspective in a way that pure numbers never could. When you think about dinosaurs, you can now anchor that thought to December 25th of the cosmic year. When you consider how long the age of dinosaurs lasted, you can remember that it occupied 1 week out of 52 weeks in cosmic time. This gives you a tool for feeling, not just knowing, the relationship between what seems vast to human perception and what actually counts as vast on cosmic scales. This timestamp also serves as a reference point for everything that comes after. If dinosaurs appeared on Christmas Day and disappeared on December 30th, then all of human evolution, from the first primates to the present moment, unfolds in the final day of the cosmic year. The entire span of recorded human history, which feels so rich and complex and full of consequence to us, occupies the final seconds of December 31st, long after the dinosaurs have come and gone. Even dominance can be brief, when the clock is this large. This insight applies not just to dinosaurs, but to every form of dominance that has ever existed or ever will exist. Geological dominance, biological dominance, technological dominance, all of it is temporary when viewed from the perspective of cosmic time. The Christmas Day appearance of dinosaurs reminds us that the cosmic year is long enough to accommodate many different experiments, many different approaches to complexity and success, many different chapters in the ongoing story of what's possible in this universe. The dinosaurs had their week. Now, in these final hours of December 31st, it's our turn. Around December 30th of our cosmic calendar, roughly 66 million years ago in real time, something happens that forever changes our understanding of how history works in the living world. The dinosaurs who have dominated Earth's landscapes for nearly a week of cosmic time suddenly disappear from the fossil record. Not gradually, not through slow decline, but abruptly, catastrophically, in what represents one of the most dramatic plot twists in the entire 4 billion year story of life on our planet. The extinction that ends the age of dinosaurs is not just another death in the long catalogue of biological mortality. It is something far more profound and far more unsettling, a reminder that even the most successful, most diverse, most seemingly permanent forms of life exist at the mercy of forces beyond their control. History, it turns out, is not only about laws and trends and gradual development. History is also about accidents, intersections, and timing. For 160 million years, dinosaurs had been the undisputed masters of terrestrial life. They had diversified into forms that filled every conceivable ecological niche. Massive herbivores that browsed treetops like living mountains, swift predators that hunted in coordinated packs, delicate creatures no larger than chickens, armored giants covered in protective spikes and plates. They had conquered land, taken to the air, and even returned to the seas. If you had been an observer during the Cretaceous period, it would have seemed obvious that dinosaurs represented the pinnacle of evolutionary success, the natural and inevitable result of millions of years of natural selection. Then, in what may have been a matter of hours or days, everything changed. An asteroid roughly 6 miles in diameter, travelling at tens of thousands of miles per hour, slammed into what is now the Yucatan Peninsula of Mexico. The impact released energy equivalent to billions of nuclear weapons, sending shockwaves around the globe, triggering massive earthquakes and tsunamis, and hurling billions of tons of debris into the atmosphere. The sky filled with dust and ash that blocked sunlight for months or years, causing a global winter that collapsed photosynthesis and devastated food chains worldwide. This is extinction as radical editor, as cosmic blue pencil that crosses out entire chapters of evolutionary experimentation with a single stroke. The asteroid impact didn't discriminate between successful and unsuccessful species, between well-adapted and poorly adapted organisms. It didn't respect the evolutionary achievements of 160 million years of dinosaurian innovation. It simply rewrote the rules of survival in ways that no amount of prior adaptation could have anticipated. But here's what makes mass extinctions so fascinating and so important to our understanding of how life works. They are not just endings, they are also beginnings. Every mass extinction event in Earth's history has been followed by an explosion of evolutionary innovation as surviving species rapidly diversify to fill the voids, ecological roles vacated by the victims. The asteroid that ended the age of dinosaurs also opened evolutionary doors that had been closed for millions of years. Small mammals, which had lived in the shadows of dinosaurs throughout the Mesozoic era, suddenly found themselves in a world with vastly expanded opportunities. Ecological niches that had been occupied by dinosaurs for over 100 million years became available overnight. Within a few million years after the extinction, mammals began to diversify into forms that would have been impossible in a dinosaur-dominated world. Large herbivores, apex predators, creatures that returned to the seas, and eventually forms that would develop the enlarged brains necessary for complex cognition and consciousness. This is contingency in action, the recognition that the history of life is shaped not only by the gradual pressures of natural selection, but also by unpredictable events that can redirect the entire course of evolution in an instant. If the asteroid had missed Earth, if it had arrived a few million years earlier or later, if it had struck a different part of the planet, the entire subsequent history of life would have unfolded differently. There might never have been large mammals. There might never have been primates. There might never have been humans capable of contemplating cosmic calendars and deep time. The extinction of the dinosaurs teaches us something unsettling but essential about the nature of existence in this universe. Nothing is inevitable until it actually happens. The evolutionary trends that seem so obvious in hindsight, the developments that appear to follow naturally from prior conditions, are all subject to interruption by events that have nothing to do with biological fitness or adaptive success. An asteroid doesn't care how well adapted you are to your current environment. A volcanic eruption doesn't respect your evolutionary achievements. A changing climate doesn't honour your species' long history of success. This fragility of the seemingly inevitable extends beyond biology into every domain of existence. The galaxies that seem so permanent and stable exist in a universe where galactic collisions are routine events. The stars that appear so reliable will eventually exhaust their nuclear fuel and die. The elements that seem so fundamental can be torn apart under extreme conditions. Even the laws of physics that govern everything might be contingent features of our particular cosmic epoch rather than eternal principles. Yet this contingency is not a cause for despair, but rather for a deeper appreciation of what actually exists. The fact that your existence depends on a chain of improbable events, including the chance extinction of the dinosaurs 66 million years ago, doesn't make your existence less meaningful. If anything, it makes your existence more remarkable, more precious, more worthy of attention and care. The December 30th extinction reminds us that we live in a universe where history is genuinely open, where the future is not determined by the past, where accident and contingency play crucial roles in shaping what becomes possible. This openness means that nothing that exists, no matter how successful or well established it seems, can take its continued existence for granted. But it also means that new possibilities can emerge from even the most catastrophic endings, and that the universe retains the capacity to surprise us, to create forms of complexity and beauty that we never could have predicted from prior conditions alone. As evening settles over December 31st of our cosmic calendar, as the final day of the cosmic year moves toward its conclusion, something new begins to stir in the post-dinosaur world. The mammals that survived the Great Extinction have spent tens of millions of years diversifying, filling ecological niches, and gradually developing forms and capabilities that would have been impossible in the shadow of the great reptiles. And now, in these evening hours of cosmic time, one particular lineage of mammals begins to experiment with something that will eventually transform not just biology, but the entire relationship between life and the universe that contains it. The first primates appear in the fossil record roughly 55 million years ago, which translates to early evening on December 31st of our cosmic calendar. These early primates are small, agile creatures living in the expanding forests of a warming world, developing enhanced vision, grasping hands, and increasingly complex social behaviors. They represent the beginning of a lineage that will eventually produce something unprecedented in the 4 billion year history of life on Earth. Minds capable of understanding their own cosmic context. But the path from early primates to human consciousness is neither straight nor inevitable. For most of the evening hours of December 31st, primates remain just another branch on the vast tree of mammalian life, successful within their ecological niche, but showing no signs of the extraordinary capabilities that will eventually emerge from their lineage. They develop better color vision, more sophisticated social structures, larger brains relative to their body size. But these changes unfold over millions of years with no clear direction toward the emergence of symbolic thought or cumulative culture. The hominin lineage, the group that includes modern humans and our extinct relatives, doesn't appear until very late in the evening, roughly 6 to 7 million years ago in real time. These early hominins are still very much like other primates in most respects, but they begin to experiment with upright walking, with using simple tools, with social cooperation on slightly larger scales. They represent the first tentative steps towards something new, but they are still recognizably part of the broader mammalian world, subject to the same ecological pressures and evolutionary constraints as their contemporaries. Anatomically modern humans, the species you belong to, don't appear until the final minutes of December 31st. The oldest fossil evidence for Homo sapiens dates back roughly 300,000 years, which represents the last few minutes of our cosmic year. From the perspective of cosmic time, your species is extraordinarily recent, arriving so late in the story that all of human history, from the first use of language to the first landing on the moon, unfolds in the thin air at the very edge of the calendar's end. But here's what makes those final minutes so remarkable. Something genuinely new emerges with modern humans, something that had never existed before in the entire history of life on Earth. Not just intelligence, because many species show evidence of problem-solving abilities, learning, and even rudimentary culture. Not just social cooperation, because countless species engage in complex cooperative behaviors. What emerges with humans is something more specific and more profound. Symbolic thought, the ability to use arbitrary signs and sounds to represent abstract concepts, and cumulative culture, the ability to store knowledge outside the individual mind and build on it across generations. This is what distinguishes your species from even the most intelligent of your evolutionary cousins. Chimpanzees can use tools, but they can't teach their offspring how to improve those tools across generations. Dolphins have complex social structures, but they can't record their social innovations in forms that persist beyond individual memory. Elephants have sophisticated emotional lives, but they can't create symbolic representations of their experiences that can be shared with elephants they've never met. Humans can do all of these things, and this capability transforms the entire dynamic of evolutionary change. For the first time in the history of life on Earth, knowledge can be accumulated, refined, and transmitted not just through genes, but through culture. Information can be stored outside the biological body in the form of language, art, written records, and eventually digital media. Each generation can build directly on the achievements of previous generations without having to rediscover everything from scratch. This is why cultural evolution can move so much faster than biological evolution. Biological innovation requires changes to DNA that must be tested over many generations through the slow process of natural selection. Cultural innovation can happen within a single generation and can spread through entire populations in decades or centuries rather than millennia. The universe does not rush, spending billions of years to produce the conditions necessary for symbolic thought, but when reflection finally emerges, reflection can move quickly. The acceleration of change in those final cosmic minutes is unprecedented in the history of the planet. In the Archinsai's space of a few 100,000 years, a blink of an eye in cosmic terms, humans develop language sophisticated enough to discuss abstract concepts, art capable of representing complex narratives, tools that can reshape entire landscapes, and social institutions that can coordinate the activities of millions of individuals. This is not just biological evolution anymore, it's something new, a hybrid of biological and cultural evolution that can produce changes on timescales that would have been impossible in the purely biological world. What emerges in those final minutes of December 31st is not a species that has transcended nature or escaped the constraints of evolutionary history. Humans remain biological beings, subject to the same physical laws and evolutionary pressures that shape all life. But they are biological beings with a new capability, the ability to understand and intentionally influence their own evolutionary trajectory, to store and share knowledge across generations, to cooperate on scales that span the entire planet. This is the context in which your own life unfolds. You exist at the moment when the universe first becomes capable of understanding itself, when matter organized into living systems develops the ability to contemplate its own origins and ultimate fate. You are not separate from cosmic history. You are cosmic history becoming aware of itself. The atoms in your body carry the signatures of stellar nucleosynthesis. The genes in your cells preserve the record of 4 billion years of evolutionary innovation. The thoughts in your mind represent the universe's first attempt to understand its own vast and ancient story. You arrive very late in cosmic time, but you arrive at the most interesting moment when the capacity for reflection finally emerges from the long chain of cosmic evolution. In the last minute of December 31st, in the final 60 seconds of our cosmic year, something extraordinary happens to the pace of change on Earth. If the entire history of the universe has unfolded with the patient rhythm of geological and biological time, measured in millions and billions of years, now suddenly everything accelerates. In this final cosmic minute, representing roughly the last few 100,000 years of real time, more innovation occurs than in many entire cosmic days that came before. This is the minute when human culture begins to accumulate momentum, when the capacity for symbolic thought and cumulative knowledge starts to transform not just human society, but the entire surface of the planet. Fire, language, art, agriculture, metalworking, writing, mathematics, philosophy, all of the foundations of what we call civilization emerge and develop within this single minute of cosmic time. It's as if the universe, having spent billions of years learning how to build stars and planets and biological complexity, suddenly discovers a new way to create complexity that operates at an entirely different speed. Fire comes first, perhaps 40 seconds into this final minute, representing the human mastery of combustion roughly 400,000 years ago. This might seem like a simple technological achievement, but fire transforms everything about how humans relate to their environment. With fire, humans can extend their active hours into the night, can cook food to extract more nutrients and make previously inedible plants digestible, can survive in climates that would otherwise be too cold for a tropical primate. Fire represents the first time that humans systematically harness energy from outside their own bodies to reshape their immediate environment. Language develops throughout this final minute, though its precise timeline remains hidden in the mists of prehistory. But by 30 seconds into the final minute, certainly by 20 seconds in, humans possess linguistic capabilities sophisticated enough to discuss abstract concepts, to share detailed knowledge about distant places and future plans, to create and transmit stories that can preserve cultural information across generations. Language represents the first technology for storing information outside individual memory, the first system that allows knowledge to accumulate beyond the limits of a single human lifetime. Art appears in the archaeological record about 15 seconds into the final minute, with cave paintings, carved figurines, and elaborate burial practices that suggest symbolic thinking has reached full flower. These early artistic expressions are not mere decoration or entertainment. They represent the first external storage systems for complex cultural information. A cave painting can preserve knowledge about animal behavior, seasonal migrations, or ceremonial practices for thousands of years. Art becomes humanity's first library, a way of encoding and transmitting knowledge that transcends the biological limits of individual memory. Agriculture emerges in the final 12 seconds of the cosmic minute, roughly 12,000 years ago in real time. This innovation represents perhaps the most dramatic transformation in human history, the shift from following the natural abundance of wild plants and animals to actively managing and reshaping entire ecosystems. Agriculture allows human populations to grow beyond anything that had been possible in hunter-gatherer societies, enables the development of permanent settlements, and creates the economic surplus necessary for specialized occupations like metalworking, pottery, and eventually writing. The development of writing systems occurs in the final 10 seconds of the cosmic minute, around 5,000 years ago. Writing represents the perfection of external information storage, allowing humans to record and preserve knowledge with a precision and permanence that far exceeds oral tradition. With writing, human culture becomes truly cumulative. Each generation can build directly on the written records of previous generations, accessing the accumulated wisdom of centuries or millennia of cultural development. Mathematics, philosophy, and systematic scientific observation emerge in the final 8 seconds, As literate civilizations develop increasingly sophisticated ways of understanding and manipulating both the natural world and abstract concepts. The Greeks develop geometry and logical reasoning. Chinese scholars create detailed astronomical records. Islamic mathematicians develop algebra. Each innovation builds on previous innovations, creating an accelerating spiral of intellectual development. This acceleration happens because cultural evolution operates by fundamentally different rules than biological evolution. Biological information is stored in DNA and can only be transmitted from parent to offspring through reproduction. Changes to this information happen slowly, through random mutations that must be tested over many generations through natural selection. Cultural information, by contrast, can be stored in language, art, writing, and other external media. It can be transmitted not just from parent to child, but from any individual to any other individual, even across vast distances and long periods of time. Cultural innovations can spread through entire populations within a single generation, and successful innovations can be deliberately improved rather than depending on random mutations. In the calendar's last minute, time is short, but meaning becomes dense. Each cosmic second now contains developments that would have been impossible in earlier epochs. The invention of agriculture in 12 cosmic seconds transforms the planet's surface more dramatically than millions of years of biological evolution. The development of writing in 10 cosmic seconds creates information storage capabilities that exceed anything achieved by biological memory systems. The emergence of systematic science in the final few cosmic seconds produces knowledge about the universe that spans from subatomic particles to galactic superclusters. This is the paradox of the final minute. By cosmic standards, it represents an almost infinitesimally brief period of time, yet it contains more innovation, more transformation, more acceleration of complexity than vast cosmic epochs that preceded it. The universe spent billions of years learning how to build the chemical and biological foundations for complex information processing. But once those foundations were in place, once matter had organized itself into structures capable of symbolic thought and cumulative culture, the pace of change shifted into an entirely new gear. You are living in the continuation of this final minute, in the ongoing acceleration that began when humans first learned to preserve knowledge outside individual memory. Every book you read, every scientific discovery you learn about, every technological innovation you use, represents the continuation of the cultural evolution that began in earnest in these final seconds of cosmic time. The smartphone in your pocket contains more information processing capability than entire civilizations possessed just a few cosmic milliseconds ago. You have access to more accumulated human knowledge than any individual in previous cosmic seconds could have imagined. The final minute teaches us that the universe does not rush through its early chapters, but when it finally produces minds capable of cumulative culture, those minds can accomplish in seconds what biology required epochs to achieve. Now we arrive at the moment that defines the entire cosmic calendar, the realization that gives this thought experiment its power to transform how you see your place in the universe. All of recorded history, everything that humanity has written down, remembered, and passed along through systematic documentation occupies only the final seconds of December 31st. Not the final minutes, not the final hour, the final seconds before the cosmic year ends. When Carl Sagan first popularized this comparison, he often described recorded history as occupying the last 10 seconds of the cosmic year, though different ways of calculating the timeline yield estimates ranging from 10 to 15 seconds. The exact number matters less than the profound compression it represents. Whether it's 10 seconds, 12 seconds, or 15 seconds, the conclusion remains the same. Everything that feels historically significant to human consciousness, everything that seems to span vast ages from our perspective, fits comfortably within the time it takes you to slowly count from 1 to 15. Let's be precise about what this means, because precision helps us feel the true weight of this compression. If we consider recorded history to begin roughly 5,000 years ago, with the earliest cuneiform tablets and hieroglyphic inscriptions, and if each cosmic second represents approximately 400 years of real time, then all of written human civilization unfolds in roughly 12.5 cosmic seconds. Every empire that has ever risen, every war that has ever been fought, every philosophy that has ever been developed, every piece of music that has ever been composed, every scientific discovery that has ever been made, all of it compressed into 12.5 seconds of cosmic time. Ancient Mesopotamia, with its ziggurats and legal codes, emerges in the final 12 seconds. The Egyptian pyramids are built in the final 11 seconds. The Golden Age of Athens, with Socrates, Plato, and Aristotle reshaping human thought, unfolds in the final 10 seconds. The Roman Empire rises, dominates the Mediterranean world, and falls, all within the final 8 seconds. The medieval period, with its cathedrals and universities and preservation of classical knowledge, occupies the final 6 seconds. The Renaissance, that explosion of art and learning and scientific curiosity that felt like a rebirth of human potential, happens in the final 3 seconds. Leonardo da Vinci paints the Mona Lisa, Michelangelo sculpts David, and Galileo turns his telescope toward the moons of Jupiter, all within the final 3 cosmic seconds. Shakespeare writes his plays, Bach composes his fugues, and Newton formulates the laws of motion and gravitation, all in the final 2.5 seconds. The Industrial Revolution, which transformed human society more dramatically than any change since the invention of agriculture, unfolds in the final 1.5 seconds. Steam engines, railroads, factories, the harnessing of electricity, the development of modern medicine, all of these innovations that reshaped civilization occur in less than 2 cosmic seconds. The entire modern world, everything that distinguishes the 21st century from previous eras, emerges in the final cosmic second. The American and French revolutions happen in the final 1.2 seconds. The abolition of slavery, the expansion of democratic institutions, and the recognition of universal human rights develop in the final 1 second. The 2 world wars, which seem to span entire eras and reshape the global order, occur within the final 0.8 seconds. The development of computers, space exploration, the internet, and modern telecommunications all emerge in the final 0.5 seconds. You were born in the final tiny fraction of the final cosmic second, in a moment so recent that it barely registers on the cosmic timeline. Your entire lifetime, from birth to this moment, occupies a span of cosmic time so brief that it approaches the limits of meaningful measurement on this scale. Every person you have ever known, every historical event you have witnessed, every technological innovation you have experienced, all of it happens in the last few milliseconds of cosmic time. This compression reveals something profound about the relationship between human experience and cosmic reality. From your perspective, history feels vast, rich, full of drama and significance. The rise and fall of civilizations, the development of science and art, the great movements of human thought and social organization, all of this seems to unfold across enormous spans of time. And from a human perspective, it does. 5,000 years represents roughly 250 human generations, enough time for countless individual stories, for the slow accumulation of knowledge, for the gradual refinement of human institutions and understanding. But when you step back to cosmic perspective, when you see this history against the backdrop of 13.8 billion years of universe evolution, something remarkable becomes visible. All of human civilization, all of recorded history, represents a sudden acceleration in the pace of change, a compressed explosion of innovation and complexity that has no precedent in the cosmic story. In 12.5 cosmic seconds, humans have gone from crude pictographs to digital communication, from simple tools to space exploration, from isolated villages to global civilization. This acceleration is unprecedented not just in human history, but in the entire history of the planet. Life spent billions of years, hundreds of cosmic days, developing the biological complexity necessary to support symbolic thought and cumulative culture. But once those capabilities emerged, once humans learned to store knowledge outside individual memory, the pace of change shifted into an entirely different gear. Cultural evolution began operating at speeds that biological evolution could never match. All of it, the entire span of empires and discoveries, wars and philosophies, art and music and literature, mathematics and science and technology, all of it compressed into the breath before midnight. This is not meant to make human history seem insignificant or trivial, quite the opposite. This compression reveals human civilization as perhaps the most remarkable phenomenon in the known universe. The emergence of complexity and knowledge and conscious purpose at a pace that defies everything we know about how change normally happens in cosmic time. The final seconds of December 31st represent not just the end of our cosmic year, but the moment when the universe first becomes capable of understanding its own history. All of recorded human history, compressed into these final seconds, represents the universe developing the capacity for self-awareness, for conscious reflection on its own vast and ancient story. After walking through the cosmic calendar from January 1st to these final seconds of December 31st, after feeling the true scale of time and recognizing how recently we arrived on the cosmic scene, you might find yourself confronting a question that strikes at the heart of human meaning. If we are so brief, so recent, such tiny flickers in the vast span of cosmic history, what does that say about the significance of our existence? Are we simply insignificant specks in an indifferent universe, or is there another way to understand what it means to be brief? This question emerges naturally from the cosmic perspective, and it deserves a thoughtful answer. The temptation, when confronted with deep time, is to assume that duration equals importance, that only things which last for cosmic ages can be considered significant. From this perspective, our brief appearance in the final seconds of the cosmic year might seem to reduce us to cosmic footnotes, interesting perhaps, but ultimately trivial compared to the vast processes that shape the universe for billions of years before we arrived. But this assumption rests on a fundamental error about the nature of value and meaning in the universe. Duration is not the same thing as significance. Importance is not measured by longevity. Some of the most profound and meaningful phenomena in the universe are also among the briefest, while some of the longest-lasting processes contribute very little to the richness and complexity of cosmic evolution. Consider the life of a mayfly, which lasts only a single day. From the perspective of cosmic time, a mayfly's existence is so brief as to be nearly instantaneous, a flash of consciousness that appears and disappears in what amounts to less than a cosmic nanosecond. Yet within that single day, that mayfly experiences an entire lifetime. Emergence from its larval stage, the drive to find a mate, the ancient dance of reproduction, the completion of a biological cycle that connects it to millions of years of evolutionary history. The mayfly's brief day contains birth, growth, purpose, and completion. Its brevity doesn't diminish the reality of its experience or its connection to the larger patterns of life. Or consider a supernova explosion, one of the most dramatic events in the cosmic catalogue. A supernova lasts only a few weeks or months, making it incredibly brief even by human standards, let alone cosmic ones. Yet in that brief explosion, a single star releases more energy than our Sun will produce over its entire 10 billion year lifetime. a supernova can outshine an entire galaxy containing hundreds of billions of stars. The elements forged in that brief stellar death will seed new star systems and eventually make possible planets, chemistry, and life itself. The brevity of the supernova doesn't diminish its cosmic significance. If anything, the compression of so much energy and consequence into such a short time makes it more remarkable, not less. Similarly, human civilization's brief appearance in the final seconds of the cosmic year doesn't diminish its significance. If anything, the concentration of so much complexity, creativity, and conscious awareness into such a brief span of time makes human existence more remarkable, not less. In these final seconds, the universe has learned to create art, music, and literature. It has developed science capable of understanding its own history. It has produced minds capable of contemplating their own place in cosmic evolution. It has generated love, compassion, curiosity, and the capacity for moral reasoning. The cosmic calendar is not an insult to human significance. It is an invitation to clarity about what kinds of significance actually matter in this universe. The calendar reveals that the most interesting and meaningful developments in cosmic history often happen quickly, in bursts of innovation and complexity that transform everything that follows. The formation of the first stars took millions of years but changed the universe forever. The emergence of life took only hundreds of millions of years, but introduced an entirely new category of cosmic process. The development of consciousness took only a few million years, but created the first observers capable of understanding cosmic history. Each of these developments was brief compared to the cosmic processes that preceded them, yet each represents a fundamental transition in the nature of cosmic evolution. Brevity, in this context, is not a sign of insignificance, but often a marker of profound innovation. The most important changes in cosmic history tend to happen quickly, in relatively brief periods when the universe discovers new ways of organizing matter, energy, and information. Your existence in these final cosmic seconds places you at the culmination of this process of cosmic innovation. You are not a late arrival to a universe that was already complete. You are a participant in the universe's most recent and perhaps most remarkable experiment in complexity and consciousness. The brevity of human history doesn't make it less significant. It makes it part of the universe's pattern of concentrated innovation, of rapid developments that reshape everything that follows. The cosmic calendar also offers perspective on the kinds of problems and concerns that dominate human attention. Many of the things that feel enormously important from within human timescales, the daily anxieties and conflicts that can consume our energy and attention, appear quite different when viewed against the backdrop of cosmic time. This perspective doesn't make these human concerns meaningless, but it can help us distinguish between the temporary and the enduring, between the local and the universal, between the problems that deserve our worry and those that might benefit from a lighter touch. At the same time, the cosmic perspective can help us appreciate the genuinely remarkable nature of ordinary human experiences. The fact that you can feel love, create beauty, understand abstract concepts, and contemplate your place in cosmic history represents the culmination of 13.8 billion years of cosmic evolution. Your capacity for consciousness, for moral reasoning, for scientific understanding, for artistic creation, all of this emerges from and contributes to the universe's growing capacity for self-awareness and self-direction. The cosmic calendar teaches us that being brief is not the same as being insignificant. That meaning emerges not from duration, but from complexity, consciousness, and connection to the larger patterns of cosmic development. You exist at the most interesting moment in cosmic history, when the universe first becomes capable of understanding itself. That's not a small thing. That's the culmination of everything that came before. Now that we understand the timeline of cosmic history and our place within it, we need to address something equally profound about your physical nature, something that connects you directly to every stage of cosmic evolution we've explored. You are not a visitor to this universe, not a stranger who somehow arrived from outside the cosmic story. You are the universe in a very literal and material sense. Every atom in your body, every molecule that makes up your cells, every element that enables your thoughts and emotions is a direct product of cosmic processes that began 13.8 billion years ago and continue to this moment. The hydrogen in your body, making up about 10% of your atomic composition, was forged in the first few minutes after the Big Bang, during those early moments of January 1st on our cosmic calendar, when the universe was hot and dense enough to fuse protons and neutrons into the lightest atomic nuclei. When you drink a glass of water, some of those hydrogen atoms date back to the very beginning of time itself. They are among the oldest things in existence, witnesses to the entire history of cosmic evolution. The carbon that forms the backbone of every organic molecule in your body, the carbon that makes possible the complex chemistry of life itself, was manufactured in the nuclear furnaces at the hearts of ancient stars. These stars lived and died billions of years before our solar system existed, fusing lighter elements into heavier ones through the nuclear processes that power stellar cores. When those stars exhausted their nuclear fuel and died in supernova explosions, they scattered this carbon throughout space, mixing it with the primordial hydrogen and helium to create the chemically enriched clouds from which our solar system eventually formed. The oxygen you breathe with every breath, the oxygen that combines with glucose in your cells to power your metabolism, was also created in stellar cores through nuclear fusion processes. The same is true for the nitrogen that makes up much of your DNA, the phosphorus in your bones and teeth, the sulfur in many of your proteins. All of these elements required the extreme conditions inside stars to be created, conditions of temperature and pressure so intense that they can force atomic nuclei to overcome their electrical repulsion and fuse together into heavier elements. The iron in your blood, the iron atoms that carry oxygen from your lungs to every cell in your body, represents an even more dramatic stellar origin. Iron is one of the most stable atomic nuclei in the universe, which means it can only be created in the cores of the most massive stars and only during the final moments of their lives when they collapse and explode as supernovae. The iron atoms in your bloodstream were forged in stellar explosions so violent that they briefly outshone entire galaxies. You carry within your circulatory system the products of some of the most energetic events in cosmic history. This is not metaphorical or poetic language. This is literal truth, confirmed by decades of research in nuclear physics, stellar evolution, and cosmology. The elements that make up your body could not have been created in any other way. The early universe lacked the chemical complexity necessary for life because it consisted almost entirely of hydrogen and helium. Every heavier element, every atom essential to your existence, had to be manufactured inside stars and scattered into space through stellar explosions before it could become incorporated into planets and eventually into living organisms. Your connection to cosmic history goes deeper than just the origins of your constituent atoms. The very structure of your body reflects billions of years of evolutionary innovation that built upon the chemical foundations provided by stellar nucleosynthesis. Your cells contain mitochondria, the descendants of ancient bacteria that learned to cooperate rather than compete, that formed partnerships which became permanent parts of every complex organism on Earth. Your DNA preserves, in its molecular structure, a record of evolutionary experiments that stretch back nearly 4 billion years to the emergence of life in Earth's primitive oceans. Your brain, the 3-pound collection of neural tissue that enables your consciousness and your ability to contemplate cosmic history, represents one of the most remarkable structures that the universe has ever produced. It contains roughly 86 billion neurons, each one connected to thousands of others through synapses, creating a network of connections that exceeds the number of stars in hundreds of galaxies. This neural network, built from elements forged in stellar cores and organized through billions of years of evolutionary development, has somehow become capable of modeling and understanding the very cosmic processes that created it. Think about the profound circularity of this situation. The universe, through a long chain of physical and biological evolution, has produced a structure, your brain, that can comprehend the universe that produced it. Hydrogen and carbon and oxygen, forged in the hearts of ancient stars, have become organized into neural networks that can contemplate the lives and deaths of stars. Matter that was once scattered through interstellar space has become concentrated into biological forms that can understand the processes of cosmic evolution, stellar nucleosynthesis, and galactic formation. Your capacity for consciousness, for abstract thought, for scientific understanding, represents the universe becoming aware of itself in one small corner of space and time. For nearly 14 billion years, cosmic evolution proceeded without any witness capable of grasping its scope and significance. Stars were born and died, galaxies formed and evolved, planets appeared and disappeared, all without any conscious observer who could appreciate the beauty and complexity of what was happening. But now, in these final seconds of the cosmic year, in your existence and the existence of other conscious beings, the universe has developed the capacity for self-reflection. When you look up at the night sky and feel wonder at the stars, you are the cosmos contemplating its own vastness. When you study the history of cosmic evolution, you are the universe learning about its own past. When you consider the future of cosmic development, you are matter and energy that emerged from the Big Bang, trying to understand where the cosmic story might lead. The cosmos does not need consciousness to continue its physical evolution. Galaxies will continue to form and merge. Stars will continue to be born and die. The fundamental forces will continue to govern the behavior of matter and energy, all regardless of whether there are any conscious observers to witness these processes. But through consciousness, through minds like yours that emerged from cosmic evolution, the universe can be known. The vast story of cosmic development can be understood, appreciated, and perhaps even consciously influenced for the first time in its long history, as we stand here in these final seconds of the cosmic year, as we recognize our recent arrival and our deep connection to the entire history of cosmic evolution. We must also confront a profound new reality about our position in this ancient story. For the first time in cosmic history, the universe has produced beings capable not just of understanding their environment, but of deliberately reshaping it on planetary and even cosmic scales. In these final seconds, we have become more than observers of cosmic evolution. We have become participants with the power to influence its future direction. This transition from observer to participant represents one of the most significant developments in the entire cosmic timeline. For nearly 14 billion years, cosmic evolution proceeded according to the laws of physics, chemistry, and biology. Stars formed and died according to nuclear physics. Planets evolved according to geological processes. Life developed according to natural selection and environmental pressures. These processes operated without conscious direction, following the natural consequences of fundamental forces and random events. But now, in these final cosmic seconds, consciousness has emerged with capabilities that can override purely natural processes. Human technology has become powerful enough to alter atmospheric composition, to redirect rivers, to create new chemical compounds that never existed in nature, to split atomic nuclei and release the energy that powers stars, to send information across the globe instantly, and to place artificial objects in orbit around other planets. For the first time in cosmic history, conscious intention has become a significant force in shaping the future of at least one planetary system. This power brings with it a responsibility that no previous generation of humans has had to contemplate. Your ancestors could live their entire lives without significantly affecting the global environment or the long-term trajectory of human development. Their tools and technologies, while locally significant, operated on scales that barely registered against the vast natural processes that govern planetary systems. But your generation, and every generation that follows, lives with technologies powerful enough to reshape the biosphere, to alter the chemical composition of the oceans and atmosphere, and to determine whether human civilization continues to develop or faces existential challenges. The cosmic calendar helps us understand why this responsibility feels so overwhelming and unfamiliar. For most of human history, for most of the final cosmic minute, humans lived as part of natural systems rather than as controllers of them. We adapted to environmental conditions rather than reshaping them to suit our preferences. Our technologies enhanced our natural capabilities without fundamentally altering the planetary systems that sustained us. This relationship between humans and their environment persisted for hundreds of thousands of years, for most of recorded history, until very recently in cosmic terms. Only in the final few cosmic seconds, roughly the last few hundred years of real time, have human technologies become powerful enough to operate on geological and atmospheric scales. The Industrial Revolution, which began less than 2 cosmic seconds ago, marked the beginning of human influence on global atmospheric chemistry. Nuclear weapons, developed less than 1 cosmic second ago, gave humans the power to release stellar-scale energies on planetary surfaces. Digital technologies, emerging in the final fractions of a cosmic second, have created global communication and coordination capabilities that can organize human activities on unprecedented scales. This acceleration of human power and influence represents an extension of the cultural evolution that has been driving change throughout the final cosmic minute. Just as the development of language, writing, and systematic knowledge allowed humans to accumulate capabilities across generations, modern technology allows each generation to build on the technological achievements of previous generations, creating tools that would have been impossible without centuries of accumulated innovation. But unlike previous technological developments, which enhanced human capabilities without fundamentally altering planetary systems, modern technologies operate on scales that affect the basic life support systems of the planet. Climate change, caused by human alteration of atmospheric chemistry, represents the first time in Earth's history that a single species has deliberately modified global environmental conditions. Nuclear weapons represent the first time that a biological species has developed the power to cause its own rapid extinction. Space exploration represents the first time that life from Earth has expanded beyond its planetary boundaries. To know the scale is to inherit a duty of care. Understanding your place in cosmic history, recognizing your deep connection to the processes that shape the universe over billions of years, carries with it an obligation to consider the consequences of human actions, not just for immediate human interests, but for the continuation of the cosmic story itself. You are not separate from cosmic evolution. You are its most recent chapter, and the choices made in these final cosmic seconds will help determine what the next chapters might contain. This responsibility is not burdensome, but rather the natural consequence of consciousness and capability. For billions of years, cosmic evolution proceeded without conscious direction, producing remarkable complexity and beauty through the interplay of natural forces and random events. Now, for the first time, conscious beings can participate in shaping cosmic evolution rather than simply being shaped by it. This represents an extraordinary opportunity as well as a profound responsibility. The cosmic perspective suggests certain approaches to this responsibility that emerge naturally from understanding deep time and our place within it. Curiosity over cynicism, because the universe has proven capable of producing remarkable innovations and beauty over cosmic time, and our brief existence offers the opportunity to contribute to rather than detract from that ongoing creativity. Stewardship over entitlement, because we are not separate from the natural world, but rather its most recent and perhaps most remarkable product. Patience over panic, because the universe operates on timescales that dwarf human anxiety, and the most profound changes often require sustained effort over periods longer than individual lifetimes. These are not moral commandments imposed from outside the cosmic story, but rather practical wisdom that emerges from understanding our actual situation within cosmic evolution. We exist at the moment when the universe first becomes capable of consciously shaping its own future development. How we handle this unprecedented capability will help determine whether consciousness becomes a permanent feature of cosmic evolution or a brief experiment that failed to sustain itself. The next cosmic seconds are unwritten, and for the first time in the universe's long history, conscious beings will play a role in determining what those seconds contain. This is not a burden to carry, but an invitation to participate in the greatest story ever told. The story of how matter and energy organized into stars, planets, life, and consciousness, and what conscious beings choose to do with their remarkable position at the leading edge of cosmic evolution. And so we return to where we began, to the image of a clock approaching midnight, to the final seconds of December 31st, as the cosmic year draws to its close. But now, having walked through all 365 days of cosmic history, having witnessed the birth of stars and galaxies, the formation of planets, the emergence of life, and the development of consciousness, you see this approaching midnight with entirely different eyes. This is not just the end of a year. It is the culmination of the most extraordinary story ever told, the story of how the universe learned to understand itself. The clock that seemed so simple at the beginning of our journey now reveals itself as an instrument of profound honesty, a timekeeper that measures not just duration but transformation, not just the passage of time but the accumulation of complexity and meaning. As midnight approaches, as the cosmic year completes its full cycle, we can see clearly what has been accomplished in these 13.8 billion years of cosmic evolution, and we can begin to imagine what might unfold in the cosmic years to come. The universe that began so simply on January 1st, hot and dense and almost featureless, has become something unrecognizably complex and beautiful. From the uniformity of the cosmic microwave background, the universe has evolved into a tapestry of galaxies and stars, planets and moons, organic molecules and living systems, conscious minds, and technological civilizations. Each cosmic month has added new layers of possibility, new forms of organization, new ways for matter and energy to interact and create patterns of increasing sophistication. Yet as our cosmic year ends, as December 31st reaches its final moments, the universe itself continues. The cosmic calendar is a human construct, a tool for understanding deep time, but cosmic evolution doesn't pause at midnight to reflect on what has been accomplished. The universe moves forward into new years, new cosmic epochs, new possibilities for development and change. Our moment is late in this particular cosmic year, but it is not necessarily final in the much longer story of cosmic development. This perspective offers both humility and hope. Humility, because it reminds us that our existence, however meaningful to us, occupies only the tiniest fraction of cosmic time, and that the universe operated for billions of years without conscious observers, and could continue to do so long after consciousness disappears. Hope, because it suggests that the universe retains vast potential for future development, that the emergence of consciousness and intelligence in these final cosmic seconds might represent not the culmination, but merely the beginning of even more remarkable forms of complexity and understanding. The cosmic calendar teaches us to hold these truths simultaneously without contradiction. We are recent arrivals in an ancient universe, yet we represent perhaps the most significant development in that universe's long history. We are temporary, lasting only microseconds in cosmic terms, yet we have achieved something unprecedented in creating minds capable of grasping cosmic scope and meaning. We are small, occupying a tiny planet orbiting an ordinary star in one galaxy among hundreds of billions. Yet we are also vast, containing within our neural networks the capacity to model and understand the entire cosmos that produced us. This paradox of cosmic perspective, the simultaneous recognition of our smallness and our significance, offers a profound gift for daily life. When you feel overwhelmed by immediate concerns, by the pressures and anxieties that can dominate human attention, remember that you exist at the culmination of 13.8 billion years of cosmic evolution, that you carry within your body the atoms forged in ancient stellar cores, that your capacity for consciousness represents the universe becoming aware of itself for the first time in its long history. When you feel disconnected from the natural world, remember that you are not separate from nature, but rather its most recent and perhaps most remarkable expression, that every breath you take connects you to the atmospheric cycles that have been operating for billions of years, that every thought you think emerges from neural processes that represent the universe's ongoing experiment with information processing and self-awareness. When you feel insignificant in the face of vast cosmic scales, remember that significance is not measured by duration or size, but by complexity, consciousness, and the capacity for understanding. The universe spent billions of years preparing the conditions necessary for minds like yours to emerge, and those minds, however briefly they exist, can comprehend and appreciate the entire cosmic story that produced them. We are recent. We have appeared only in the final seconds of the cosmic year, after nearly all of cosmic history has already unfolded. Our species is younger than many mountain ranges, younger than the oldest trees, younger than ice sheets that have waxed and waned across geological time. From the perspective of deep time, human civilization is a recent experiment, consciousness is a late innovation, and our individual lives are almost infinitesimally brief flickers of awareness. We are temporary. We will not persist forever, not as individuals, not as a species, not even as a planet or a solar system. The universe that produced us will continue to evolve long after we have returned to the cosmic dust from which we came. Stars will continue to shine and die, galaxies will continue to merge and separate, the fundamental forces will continue to govern the behavior of matter and energy across scales we can barely imagine. And yet, we can understand. In these final seconds of the cosmic year, matter has organized itself into structures capable of contemplating their own origins and ultimate fate. Hydrogen and carbon atoms, forged in stellar cores billions of years ago, have become arranged into neural networks that can trace the history of cosmic evolution from the Big Bang to the present moment. The universe has learned to ask questions about itself, to wonder about its own nature, to search for meaning in its own vast and ancient story. In the last seconds of the year, in your existence and the existence of other conscious beings, the universe has learned to ask what time it is. This capacity for temporal self-awareness, for understanding our place in cosmic history, represents perhaps the most remarkable achievement in the known universe. Consciousness that can grasp its own cosmic context and find meaning not despite its brevity, but because of its unique position at the leading edge of cosmic evolution, where matter first becomes aware of the magnificent story of its own development across deep time.